Okay, hello everyone. So I'll be giving a brief introduction about the Cadence Virtuoso. So first of all, for instantiating, for instantiating any transistor, you could use the shortcut I, and then you have to select the library that you are using. For example, if I am using CMOS 65 library, I'll select it, and then the transistor that I want. For example, NSVTLP, sorry, NSVTLP. Then I give a enter, hide, and I have this. So let's say I place this, escape, and then I click on it, press Q. Q will give the object properties. You can change the width and length here. So this was the thing. And okay, let me delete this. Okay, this is one thing. And then in the analog assignment that you have been given, you also need the current sources, DC voltage source, the VDD and ground connections. So for that, again, you have to press I. Now, in this case, you have to move to the analog LIB. Click on it. And then, for example, for VDD, just press VDD and you'll get something like this. So this is for VDD. Again, press I. For ground, press GND and you will get a connection like this, which is named as ground. For undoing things, use the shortcut U. Okay. Now, for creating or connections or wires, press W. For example, if I want to connect this wire to the ground, I would just give a single press. Then wherever I want to bend it, I'll again press once and then again one more press, and finally this node out node is connected to ground, but I don't want it, so I'll undo it. U. Okay. Now how do I get this voltage source? Again, press I, the same library, analog lib VDC. Now this will give me the voltage source, required voltage source, DC voltage source. Press Q again, you'll get the properties. This is the DC voltage. For example, I am giving the demo in 65 nanometers. So the DC voltage could be from 1 volt to 1.32 or somewhere in that range. So let me take 1.2 volt as the DC voltage. Other things are not required, and that's enough. Press OK and it'll be there. But I again don't want it. For current source again, uh, sorry, again you press IDC and you get this current source. Again, you have to like give the DC current value here and press OK. That is it. And for example, when you are making the schematic, instead of placing wires here and there, what you can do is you can use label. For example, if you could see at this node out, instead of, so basically what I want is to connect this node to out, this out to out. So instead of like taking a wire from here to this point, what I have done is I've used the label. So how do I get to a label? I could move to create. Sorry. Okay, let's move to the shortcut command. For label, the shortcut command is L. Press L. For example, if I want the node name as out, I'll click out. Then I'll cut it. And then I'll press at that node which I want. For example, let's say this node I want to connect with this line. So I'll click here. Okay. Now these two are connected. Internally, these two are connected, but yeah. So the schematic looks slightly better in this case. Okay. So the circuit is a cascode current mirror, as you might know, right? And I have made a simulation setup. So basically, the VDD is connected to 1.2 volt. So the connection could be given something like this. This is VDD, this is ground, and in between we have the VDC source of 1.2. Uh, okay, now this is VDD. This is a current source of 10 micro. This goes through this, and this is the normal structure that we have. Uh, okay, and again on the other arm that is here in this branch, what we do is we connect this out to this node, and then we have a VDC bias voltage, and then we have VDD. Right. And one thing I want to point out is these bodies are connected to the source, which should not be done. But for simulation sake, I have taken it in this manner. So okay, I've taken the size randomly, but you have to calculate it, obviously. Uh, okay, now after creating this layout, sorry, schematic, let's save it. Okay, ADEL session. Uh, Now I come to this window, ADEL window. So the first thing is move to artistic K, set up the corners, save model, save scenario. It is saved. You need to cut it. Then if there are any variables here, for example, instead of this VDC, which is basically uh, without giving a like constant value of let's say 600 millivolt or something, I've given a variable V bias, right? So there might be other variables here. So to get those variable from the cell view, this is the method. I get the value from the cell view. Now I give a random value. I'm giving a random value, but again, you have to calculate it. So I've taken 500 millivolt. Okay. Now the simulation which I want to do is DC simulation. So I'll select the DC, save DC operating point. I will click here. I'll not select anything and enable. Okay. So this is selected, and then I'll run. So, okay, there are no errors here. We can ignore the warnings. Okay. Now to see the operating points, go to results. Firstly, go to results in the ADEL window, print DC operating points. Now I have to just click on the transistor of which I want to see the parameters like IG, uh, no, GM, and all those parameters. So for example, I will click on the, let's say M3. I'll click on this. And as I click, I get the parameters resulted. So, okay, here I have the GM value. I have the IDS value, which is 9.885 micro. Then we have the early voltage, VTH, threshold voltage. And this is region. Region 1 means that it is in linear region. Region 2 means that the device is in saturation region. And region 0 means the device is in cutoff region. So you could like just search it up in the web and you will get more information about the regions in Cadence. Okay, so we have this. You can find the currents and the different parameters here, GMB. And one more important thing that you can get is the beta effective. Now, beta effective means the mu and COX value, mu and COX value, uh, which is multiplied with the width and length of the device. So this is one thing, and yeah, okay. So basically, the idea of DC simulation is to set up the bias. So you could like directly move to R and check whether it is in saturation or not. In this case, it is not. Okay. Now let's check it for M0. Directly, let's move to our region. So you can just select anything and click the thing that you want. For example, in this case, I want region, which is starting from R. So I'll click R region. Region 2 means it's in saturation. And these two devices are obviously in saturation. So we don't want to check them. And yeah, so this is all about DC simulation. For example, if you want the parameter value, let's say I don't have any parameter value for a NMOS. I want the lambda, I want the mu and cox, and let's say I want uh, parameters on similar lines. So what I could do is just run a DC simulation, click on it, and get the lambda value. So yeah. So yeah, the lambda value is not there, but early voltage is there. So early voltage reciprocal of that gives the lambda. So yeah, early. Let's press E. Oh, what? Okay, sorry. Okay, so we have the early voltage as 6.737. So just an inverse of it will give the uh, lambda. Then we have the VDS also. Uh, R out again. We have this. So in this manner, you could get the parameters that you want to start with the design. Now, let's say uh, I have simulated the circuit. What I found was that my M3 is not in saturation. It is in triode. But in cascode current mirror, what I want is that all the transistors should be in saturation. So what should I do? Maybe what I can do is I could vary this VDC, this bias voltage, and maybe then check whether I'm getting the IOT to be similar to 10 micro. Because if I get a similar value with respect to the I reference, that means that more or less my transistors are in saturation. So okay, again, okay, sorry, ADL is open. So I'll just click on it. I'll click on the DC simulation, right click, edit. Now what I'll do is component design, sorry, design variable and component design parameter. These are two important things when we talk about sweeps. So for now, we want component parameter that is, okay, let's select it first. So, okay, DC, VDC. So we have selected this. So basically, we are sweeping this VDC, which is named as V bias here in our case. So where should we sweep it from? 0 to, let's say 1.2. Okay. And now basically I want to plot something, right? So for that, what I will do is outputs to be plotted, select on design, or I could go to this point, right? This point from design. And what do I want? I want this one. Sorry, I want the current. So basically I have to double click it so that this current, drain current is selected. But by mistake, I selected all this. So basically I have to delete it from. So this out is a voltage. It's not a current. So I'll delete it. I want only the D, M3. I want the value at M3's drain, current value at M3's drain. So I'll select it, and the other three I'll delete, and delete. Okay. So I have the things that I want. So basically now what will happen is I'll have a plot of current, that is the drain current of M3 with respect to the voltage. And which voltage is it? It is the VDC voltage of this. So basically this will be placed over this here. So you could just run the simulation and we have the value. So V, by pressing V, we'll have the vertical bar, and just by moving it, you could see that as the voltage of the V bias is reducing, we have a better current source. So let's say around at 400 millivolt, we are getting 9.95, which is fairly equivalent to 10 micro with some error in it. So 400 is a better value, 400 millivolt. 500 is also giving us a near value, but in that range, the M3 is in triode, which we don't want. So 400 is the voltage that we are expecting. So let's minimize it. Now with 400 millivolt, I'll run a DC simulation again. 400, edit it. I don't want to sweep the value. So component parameter will be unchecked. Okay, now okay. Right, right. Okay. Now in this case, I'll not get a graph in DC simulation. So I have to move to results, print, DC output, click on M3. Again, randomly click on this result display, press R. I don't want R out as of now. R, R. So still it is in region. Okay. Okay. So the process is sort of hit and trial. So I'll make this 300 and again check it. Again print. Sorry. Result. Direct print. Yeah. Now this is in region 2. Oh, yeah. So now this is in saturation, and now basically I could get the uh, now since this is in saturation, so that means more or less this 10 micro is replicated at this out port or pin, and all the transistors in the cascode are also in saturation. So I satisfy all my conditions. Now again basically ADL window, and this case I want to calculate the R out, that is output resistance. Okay. So for calculating that, what I'll have to do is